This lesson is on isotopes and average atomic mass. You will recall from your previous studies in chemistry that an atom is made up of three subatomic particles, subatomic meaning smaller than the atom, namely electrons, neutrons, and protons. You will also recall that electrons are negatively charged and are found in energy levels outside the nucleus. Neutrons have no charge and they're found inside the nucleus, and protons have a positive charge and they're also found inside the nucleus. You will also remember that when you're drawing this diagram, which is known as the Bohr-Rutherford diagram, each energy level holds a specific number of electrons. You will also remember the terms atomic number and mass number. Atomic number and mass number refer to the number of protons, neutrons, and electrons. Atomic number is the number of protons inside the atom, and that is typically written on the left-hand side of the symbol. So here's an example right here. Carbon has an atomic number of 6, which tells me that it has 6 protons. The mass number is represented by the letter A here, is the number of protons and neutrons. When we are looking at an element, the mass number is typically written on the top left-hand corner. And in this case, since that's protons and neutrons, I know that carbon has 6 neutrons. If you don't remember how to find the number of neutrons, it's basically mass number minus atomic number. The number of electrons is the same as the number of protons as long as the atom has no charge. In this case, the carbon that's written has no charge. If carbon had a charge, there would be a number on the top right-hand corner, and that number would either be negative or positive. If you don't remember charged atoms, which are also known as ions, you can watch a video on ions. This video mainly deals with isotopes. Here I have 3 isotopes of carbon. These are all carbon atoms. How do I know they're all carbon atoms? Because if you count the number of protons, in this case these are represented by these green circles, you will see that each carbon atom that's shown here has 6 protons. If an atom has 6 protons, it can only be carbon. The number of protons identifies the element. If the element had 7 protons, it wouldn't be carbon anymore, it would be nitrogen. However, one of the things you notice here is when I look at these 3 diagrams that I've shown you, these 3 versions of carbon that I've shown you, is that they have different number of neutrons. This one has 6 neutrons, this one has 7 neutrons, and this one has 8 neutrons, which obviously gives them different mass numbers. So this one will have a mass number of 12. This one will have a mass number of 13. This one will have a mass number of 14. So you can think of these as identical carbon atoms with slightly heavier masses. Now, why does this happen? This is just nature. We find these in nature. Carbon has 3 isotopes. We say that carbon has 3 isotopes, carbon 12, carbon 13, and carbon 14. Notice that the number of electrons is also the same as the number of protons, just like we learned in the last slide. So how do we describe isotopes then? Isotopes are atoms of the same element, which means they have the same number of protons with different number of neutrons or mass numbers. So this again is the carbon atoms that I showed you on the last slide. This is carbon 12. We generally represent it like that. This is one isotope of carbon. This is carbon 13, and this is carbon 14. These are all carbon because they all have the same number of protons. However, when you do quick math here, you'll see that they have different number of neutrons. Here are 3 isotopes of magnesium. Magnesium has 12 protons. And when you take a look at the mass numbers, you can see that they have different mass numbers. This one has 12 neutrons. This one will have 13 neutrons. And this one will have 14 neutrons. I'm coming up with these by just subtracting these 2 numbers here. These are now isotopes of magnesium. The next thing we're going to talk about is something called isotopic abundance. Abundance in English basically means how common something is. In this case, we're dealing with the abundance of a specific isotope. This is a piece of magnesium metal. When you magnify a small section of it, you see here that these 3 isotopes of magnesium are all actually present in that sample of magnesium. However, if you count the number of circles here, you'll see that I actually have more magnesium 24 than the other 2. You can sit here and actually count them and put the numbers as a percentage, but I've already done that for you. The amount of magnesium 24 that you have in relation to the 25 and the 26 can be represented as a percentage, and that's what we call percentage abundance. You can see magnesium 24 is 78.7%, which basically means that anytime you find magnesium in nature, the most common version that you will find will be the magnesium 24. Magnesium 25 is 10.1%, and magnesium 26 is 11.2%. If you quickly add these up, these all add up to 100%. So, what is abundance? Abundance basically tells you which isotope is more common or more abundant. Now, why is that important? Because you will see that when we find the mass of magnesium, all of these three isotopes, because they're all present in the sample of magnesium, we have to average their masses to get to the mass of magnesium. I'll explain what I mean by that. How do we find the isotopes of an element? We use something called a mass spectrometer, this machine here. It's a big machine. And essentially what you do is you put your sample in here and you hit it with a beam of electrons. You also vaporize it. And then there's a magnetic field. What happens is that the sample or the element becomes positively charged. You don't need to worry about that. And then it goes through a magnetic field, and the magnetic field, based on its size and charge, will separate them, and then there is a detector at the end. The detector will produce a graph that looks like this, which we call a mass spectrum. The mass spectrum will have peaks in it. In this case, these are vertical peaks. The number of peaks tells you the number of isotopes. In this case, this is magnesium. So by looking at these peaks, I can see that magnesium has three isotopes. They're magnesium 24, 25, and 26. How did I come up with the masses? You will see that those masses are determined from the numbers on the x-axis. This is known as mass to charge ratio. You don't have to worry about that. You can just think of these as mass. The height of the peak tells you the abundance. I can tell here that magnesium 24 is the most abundant of all of them. Average atomic mass. This is going to be important for you in grade 11 or in grade 10. Basically, average atomic mass is the mass that's listed in the periodic table. This mass is the average of the masses of all three of these isotopes. If you take a look at individual isotopes, they have masses that are whole numbers. These are mass numbers. And all three of these are present in a sample of an element. So in this case, when I find a sample of carbon in nature, all three of these isotopes are actually present in there. So when I ask you, what is the mass of carbon? Well, the mass of carbon is not just the mass of one isotope, it's the mass of all of these isotopes combined. So we call that average atomic mass. This is the mass that's listed in the periodic table as the average of the masses of all isotopes. Now, normally when we find average, we will take 12 plus 13 plus 14 and we will divide it by 3. However, you will see very quickly that we cannot do that here because of these abundances. In this particular case here, the isotope that contributes the most towards the mass of carbon is this one, because carbon is made up mainly of carbon-12. Here's how we calculate average atomic mass. So the atomic mass of an element, or the average atomic mass of an element, is calculated by multiplying the fractional abundance. Fractional abundance basically means that you take that percent abundance and you convert it to a decimal form. I'll show you an example. Multiplied by the mass of the isotope plus the fractional abundance of isotope 2 times the mass of the isotope 2. If an element had 5 isotopes, I would just repeat this 5 times. In this case, this shows the calculation for 2 isotopes. So let's take a look at an example here. We want to find the average atomic mass of carbon. Carbon has 3 isotopes, and here are the abundances. So the formula tells me take the fractional abundance of isotope 1. So in this case, my abundance is 98.9%. I'm going to convert that into a decimal. How do I do that? You divide by 100. So that 98.9 becomes 0.989 times 12, which is the atomic mass or the mass number of that specific isotope. Here is the fractional abundance, or the decimal form of the abundance of this carbon, and so on and so forth. And you will see that if you actually quickly calculate that, the atomic mass is 12.01. And this is the mass that is found in the periodic table. The next question we're going to do is calculating the abundance, giving the average atomic mass of an element. And this is a little bit harder to do. So in this case, if I gave you the fractional abundance, in this case, if I gave you the atomic mass or the average atomic mass, and I gave you the mass of this isotope and mass of that isotope, and I asked you to find the abundance of each, how would we go about doing that? This involves a little bit more math, but let's take a look at a quick example. So in this case, the question says that we're dealing with copper, which has two isotopes, copper 63 and copper 65, and they have also given you the mass of copper, which is listed in the periodic table, 63.5. This is average atomic mass. In our previous example, we were finding the average atomic mass. Here, you are given the average atomic mass, and you're given the masses of each isotope, and I'm asking you to find their abundance. Now, here's the key thing to remember here. I have two unknowns. When it comes to math and you have two unknowns, you write some kind of a relationship which relates the two of them. So in this case, I'm going to say let the letter X represent the abundance of copper 63. Why am I doing this? Well, there's no other way to do this. Of course, you can use more math. However, I have two unknowns. So the one thing you will remember is that these abundances, when I find their abundances, the abundances of those two isotopes will add up to 100%. So if I let one of them be X, then the other one can be written as 100 minus X, or it can be written as 1 minus X if I was using the fractional version of the abundance. So here's the key. You let the abundance of one of these isotopes be represented by the letter X, and the other one will be 1 minus X or 100 minus X. Why? Because those two isotopes will add up to 100%. All right, now we can do the math. If I continue using the same formula, in this case, I'm going to place the atomic mass, the average atomic mass of copper here, because that's here on the left-hand side of the equal sign. Fractional abundance, in this case, I don't know what it is, so I'm letting the fractional abundance of copper 63 be X, and then the fractional abundance of the second isotope be 1 minus X. Why? Well, we just talked about that. All right, when you quickly solve these and you open them up using math, you can see here that X is 0.75 or 75%. So what have we just discovered here? X being the abundance of copper 63, it tells me that copper 63 has an abundance of 75% and copper 65 has an abundance of 25%.